All right, welcome to the Explainer. Today, we are diving into one of the absolute cornerstones of data science, linear regression. Now, it might sound basic, but trust me, getting a real handle on this is your ticket to understanding pretty much everything else in machine learning.
So let's just jump right in. We are swimming in an ocean of data, right? But most of it, it's just noise. It's messy, it's chaotic. So the huge central question for anyone working with data is this: how do you possibly find the real pattern, the actual signal that's buried deep inside all of that random static?
Well, that hunt has a name. It's called statistical learning, and you should really think of it like being a detective. The whole mission is to find this unknown secret formula. We call it F, that perfectly connects your inputs, the X's, to your outputs, the Y's. It's the hidden relationship we're trying to expose.
And this right here, this is where it all starts. The core idea can be boiled down to this one equation. Y equals f of x plus epsilon. Okay, so y is the thing we want to predict, like sales. Easy enough. Then you have f of x. That's the signal, the true perfect relationship we're hunting for, like how every dollar spent on ads actually affects sales. And that little Greek letter at the end, epsilon, that's the noise. It's all the random stuff, the chaos we can never predict or control.
But, and this is a big but, in the real world, that F function isn't some nice, clean equation. No way. It's almost always a ridiculously tangled mess. Trying to figure out its exact shape, especially when you're juggling hundreds of variables, is practically impossible. It's like you're hitting a giant wall.
And that wall has a pretty cool, dramatic name, the curse of dimensionality. Here's what it means. Every time you add another variable, another dimension, the space that your data lives in just explodes in size. Your data points get spread out so far from each other that the whole idea of nearby points kind of stops meaning anything. It becomes impossible to see what's going on.
So, to get around this curse, data scientists basically have two main paths they can take. On one side, you have parametric methods. These are the ones that make a big, bold assumption about the shape of F. They might just say, you know what? Let's just assume it's a straight line. This makes the problem way simpler. On the other side, you've got non-parametric methods. These make zero assumptions. They just try to hug the data as closely as possible, which is flexible, but man, it can get complicated fast and needs a ton of data.
For today, we're going down that first path, the parametric one. And on this path, we're going to meet our hero, a simple but shockingly powerful assumption.
And here it is, simple linear regression. The heroic assumption is this: we're just going to pretend that complicated, messy relationship between x and y is a straight line, period. And just like that, our massive, impossible problem shrinks down to something we can actually solve, just finding two numbers, an intercept, which we call beta naught, and a slope, beta 1. That's it.
Okay, great. So we've decided to use a line. But that brings up a new problem, right? I mean, if you look at a scatter plot of data, you could draw, what, a million? An infinite number of lines through it. So how on earth do we figure out which single one of those is the best one?
The answer is a really clever and, honestly, pretty intuitive technique called the method of least squares. Let's break down how it works.
The whole logic starts with a really simple idea. A good line is a line that's as close to the real data points as possible. So for every single data point we have, we measure the vertical distance, that little gap, between the real value and the point on our line. Each one of those little errors has a name. We call them residuals.
So just to be super clear, a residual is just the prediction error for one single data point. It's that gap between what actually happened, y, and what our line predicted would happen, which we call y hat.
So here's how the method finds the best line. First, you just draw any old line. Then you calculate that residual for every single data point. Now here comes the magic trick. You square every single one of those residuals. This is so smart because it gets rid of any negative values and, more importantly, it punishes big errors way more than small errors. After that, you just add up all those squared values to get one number called the residual sum of squares, or RSS. And the final step, you find the one single line that makes that RSS number as tiny as it can possibly be. That line is your winner.
So, our hero, the straight line, has a way to find the perfect fit. Awesome. Problem solved, right? Well, not so fast. Because choosing a simple hero comes with a huge, unavoidable trade-off. It's time for a reality check.
Look, a straight line is powerful because of its simplicity. But let's be honest, the real world is almost never that simple. The connection between two things is rarely a perfect line. And this gap, this difference between our simple model and the complex reality, creates this fundamental tension that exists in all of machine learning.
And that tension is called the bias-variance trade-off. Bias is basically the error you get by trying to fit a simple model, like a line, to a complicated real-world problem. You can think of it as the error from being too simple. Variance, on the other hand, is about how much your line would jump around if you tried to fit it to a different sample of data. It's the error from being too sensitive.
So let's connect that back to our hero. A really inflexible model, like linear regression, is super stable. It doesn't change much. That means it has low variance. But because it's so simple, it might totally miss the real curvy pattern in the data, which means it can have high bias. Now, a super flexible model could trace that curvy pattern perfectly, giving it low bias, but it might be so sensitive that it ends up just memorizing the noise, giving it high variance.
And this chart really visualizes the whole thing perfectly. On the left, with our simple model, bias is high but variance is low. All the way on the right, with a super complex model, bias is low but variance is high. But the goal isn't to be at either end. The bullseye, the sweet spot, is right there in the middle, at that perfect level of flexibility, where the total error is at its absolute lowest point.
So here's the absolute key takeaway. The goal is not to get zero bias or zero variance. You can't. They're locked in this constant tug of war. The real goal, the art of this whole game, is to find the perfect balance between them that minimizes the total error when you use your model on brand new data it's never seen before.
So it all comes down to this. For any given problem, there is one optimal level of flexibility that gets you the lowest possible error. Not too simple, not too complex, just right.
This all leads to maybe my favorite quote in all of statistics from a guy named George Box. He said, essentially, all models are wrong, but some are useful. Our straight line model is technically wrong. The world isn't a perfect line. But by making that wrong assumption, it becomes an incredibly useful tool for finding that signal hidden in all the noise.
Which leaves us with one final question for you to think about. Now that you understand this fundamental trade-off, this push and pull between a model being simple and being flexible, the real question is, when is choosing that simple, technically wrong model not just an okay choice, but actually the smartest, most useful choice you can possibly make?